So now being recorded. So welcome back, everybody. So I think I want to start with a quick recap of everything we've done so far, because today we're going to start with a new topic. So this is just a quick recap. Just first, I'll share the screen. That might help. Yeah. Okay. Also, one more thing. So, I mean, we're going to post soon, probably later today, on Piazza, on the website and on Piazza, the Gradescope instructions. So, if you've never used, I assume most of you use Gradescope in the past. I mean, this is how you submit homeworks, how we grade them, how you get them back. So, you get instructions on the website later today. Okay, so again, starting to recap, and I'll actually see what I'm typing. Okay, recap. So far we discussed several notions of expansion. So we discussed, for the most part, we discussed edge expansion, which is a combinatorial notion, and we discussed spectral expansion, which is a linear algebraic notion. And we've seen various ways of connecting them, right? So that these two things are basically the same. And we saw two formal ways of connecting them. One was the expander mixing lemma. And other one was Chigger, or Chigger's inequality. So two different ways of connecting notions of edge expansion and spectral expansion. And we also saw that spectral expansion has a lot of connections with analyzing random walks and expanders. So that it gives us a very natural way of analyzing them, studying them. And the last thing we sort of briefly mentioned, but we didn't really discuss so far in detail, was the notion of a vertex expanders or vertex expansion. So far we just sort of, if you remember in the first lecture, we just defined it, but we didn't discuss its sense. But today we're actually going to discuss vertex expansion to greater depth, and because it's going to be very connected to applications. So the plan for this week is as follows: is today, well, in general, this week we're going to talk about two different applications where expanders play a pivotal role. But these applications might not seem like they have anything to do with expanders, but actually expanders are crucial in them. So today is going to be about questions about low bounds in linear algebra. And on Thursday, we talk about error correcting codes. And the reasons that we chose to present these two applications is, first of all, I think they're very different than the applications we saw so far, but also both of them rely on sort of notions of vertex expansion. And I just wanted to sort of, and in particular, these are going to be notions that it might not seem obvious when we're going to introduce it, but they're going to be different from edge expansion. So in particular, when we're going to discuss, constructions of expanders in week 5, and we're going to show you two different constructions. One is algebraic, and one is combinatorial. They both naturally are going to construct spectral expanders. And we know spectral expanders are very connected to edge expanders, and they're also somewhat connected to vertex expanders, but not quite the same way. So to construct vertex expanders, we need sometimes different ways. So for example, the combinatorial construction I'm going to show you, called the zigzag construction, can give vertex expanders, but the algebraic constructions that we're going to show you, like the Morgulis ones or the Lubozzi-Philipp-Salomon one we discussed, we don't know that they give vertex expanders. So there's still a bit of mystery in how can we get vertex expanders using algebraic construction. This is still, as far as I know, is open. But the algebraic construction can give you that. so it's flexible enough so that you can adapt them to whatever notion of expansion you need for your application. So that's a plan for this week. So maybe now is a good time to see if anybody has any questions on what we covered so far or on the plan for this week before I start talking about, the concrete application of today. No, okay. So again, the plan for today is this low bounds linear algebra. So what do we mean by linear algebra? So in general, I mean, you want to compute y equal ax. So imagine A is some maybe n by n matrix, and x and y are vectors in your favorite field, f to the n. So f could be maybe binary field, could be real numbers, could be complex numbers, could be finite fields, could be whatever you want. And the question is, how many operations do we need to compute ax? So imagine A. So what is the input here? So let's see, that's important. If I give you the input to be A, then just reading A will take you n squared time, because it's an n by n matrix. So I'm thinking here as A, the input here is x. A in the matrix, A sort of defines the question, defines the problem, let's say. So I'll give you an example in a second, but don't think of A as being part of your input. Think of X as being your input, and A is something prefixed, predefined matrix that you want to compute. So maybe let's do an example. Let's want to illustrate it. By the way, there's another question: how do we measure operations? So I'll show you a concrete model in a second, but for now, just think about it conceptually. So the example I want to tell you was the FFT, the first Fourier transform. So I'm sure all of you heard about FFT, and you know how it's sort of crucial in many applications for digital signal processing, analog, GPS everywhere. And so FFT has the following very specific metrics. So it's going to be an n by n matrix, where the entry, the ij entry to A is going to have the following very specific entry. It's going to be right like that, omega n to the I. Maybe I won't use I. I is maybe going to be not a good letter to use here. Let's put AB, where omega n is an nth root of unity, the complex nth root of unity, and concretely it's e to the 2 pi I over n. So again, I'm assuming most of you have seen the FFT matrix before, but even if you haven't, it doesn't really matter. It's a concrete matrix, it's given here. So it's not part of your input. And the question is, what does it mean to compute the Fourier transform of a vector? It's exactly computing A times X. So we're thinking of X. So again, we have this input, which is X in this case, which is going to be maybe a complex number. But again, think of it as giving some finite precision, or maybe it's even in short, small integers, doesn't really matter. And your goal is to compute AX. And there's this so in general, you can ask, well, how fast can you compute it? So for FFT, the answer is order n log n. So you can do it really fast, in almost linear time. And this is actually one of the main reasons why FFT called fast, because this matrix is really what's called a discrete Fourier transform matrix. So really, this is a DFT matrix. And the algorithm that multiplied A times X super fast in near linear time is called the fast Fourier transform. And this is really the main reason why you can use Fourier transform for real life applications. Because so here's another fact. For most matrices, let's say most n by n, A, so you need something like n squared over maybe log n time to compute AX. So if I give you a random matrix A, just an arbitrary matrix A, then for most such matrices, there is no fast way of computing A times X. So I still haven't defined the actual computational model. I'll do it in the next few minutes. But I just want to point out that, for generic matrices, we need essentially quadratic time to multiply by A, while FFT is sort of special. It has a special structure, and we can do it in near linear time. And the question is why? So there are two questions that we will try to understand. So maybe the first questions. So maybe first what we need is just to define formal model, right? So that how good do we actually capture, computations? How many steps do we do? So we'll do that. Then we want to ask questions like, can FFT be computed faster than order n again? Why is that interesting? Well, order n is necessary just to read the inputs. But if you can, let's say, improve n log n to n log n, or to linear in n, like in application, it will save a huge factor. It's a log n factor if n is big. That would have dramatic effects. Also, if we can prove this is impossible, it's also going to be a major milestone, because currently we don't have techniques to prove super linear lower bounds for such questions. So even though we know that for most matrices A, you need essentially quadratic time, we don't know how to prove it for concrete matrices A. So I put as a third question here, prove for some explicit matrix A, a lower bound of, something omega of n, meaning something super linear in n, n log n, n log n, anything. Like, we don't know how to do that. But what I want to tell you is about some investigation that Leslie Valiant did probably 30 years ago into this question that led very naturally into sort of applications of expanders. So far, I haven't defined the model formally, but I want to see if anybody has any questions on this informal level. No? Okay. So maybe the next step will be to define the model formally. So we want a formal model for arithmetic operations, or for arithmetic computation. Now, the model that we're going to study is something that's called arithmetic circuits. So let me first show you an example. So what's an arithmetic circuit? It's like any Boolean circuit. Maybe you have basic operations, basic gates. You can do very simple computations, and you want to concatenate them or combine them to compute the computation we're trying to do. Now, in our case, we just want to do linear computation. So we only do additions and subtractions and linear operations. More generally, if you would like to compute something that's a polynomial, we'll also need to allow multiplication. But for our specific application, we don't need to do that. So I'll just restrict our attention to just doing linear operations, just additions, subtractions, maybe with coefficients, but without any multiplication. We won't need them. So maybe let's start with an example. So let's say I have 4 inputs. No, maybe use a different color here. So I have x1, x2, x3, x4, and I have maybe 4 outputs: y1, y2, y3, y4, and maybe here I'll define gates. So gates, maybe here's going to be a gate. It's going to be class. Oh, sorry. Maybe that's going to be a class gate that will compute x1 plus x2. Maybe here I have another class gate. There's some. And maybe here I'm going to have something that's going to have some coefficients. I might allow some coefficients, like maybe here I'll denote this gate by maybe its input. Let's call this input z1 and z2. Maybe z1 plus 2z2. I can connect them. And maybe now I connect them like that. Okay, maybe that's just an example. So this would be an example of an arithmetic circuit. So again, everything here, so all the information flows from the bottom to the top. So the input is x. The inputs are, x1 to x4. And what are the outputs? Let's see. So y1 is going to be x1. Y2 is going to be x1 plus x2. Y3 is going to be, well, x1 plus x2 plus 2x3 plus 2x4. And y4 is going to be x3 plus x4. Right, so this is with the linear computation, or with the linear transformation we compute here. And notice that, even though I have like 4 inputs and 4 outputs, I only need like 3 internal nodes to this computation, right? So we'll define the size of this definition. That's an arithmetic circuit. In this case, I'll define the size of it to be the number of nodes. Which I guess in this case, you can think, it doesn't really matter if we identify the inputs or outputs as nodes or not, just another 2n. So either way you want to define it's fine, but the size is just going to be the number of nodes in this circuit. Okay, so now let's maybe define this a bit more formally. But is this example clear? So what is the formal definition? So it's going to be so an arithmetic circuit is a directed acyclic graph, right? So it's going to have its inputs corresponds to nodes without in edges, right? Like x1, x2, x3, x4 here. The outputs are nodes without out edges, like y1, y2, y3, y4 here. And all the internal nodes compute some, let's call it 2 sparse linear combination. So they compute something like alpha z1 plus beta z2 for some alpha and beta field. So an internal node has 2 inputs that we call z1 and z2, and it comes hardwired with 2 coefficients alpha and beta, and it computes this specific linear combination. And overall, an arithmetic circuit, so let's call it so an arithmetic circuit, let's call it C, computes a linear map, right? C maps F. Let's say if I have n inputs and m outputs, it computes Fn to Fm. Okay. So again, I hope that this, at this level, I hope everything is clear. So now we have a formal model. So we say, yeah, we cannot compute everything in a single shot. A gate, we're assuming we can take 2 inputs and compute a 2 sparse linear combination of them in a single shot. That'd be 1 operation. And they want to do it iteratively. So to compute such a circuit, you go from the inputs to the outputs by let's say some topological order, and you just compute it 1 by 1. Right. So the size of the circuit, like we said, so the size of C is just a number of nodes. And now we can sort of go back to this fact I told you before. So here's a fact. If we have time towards the end of class, I'll prove it. If not, then it's an exercise. So for random, so if A is a random n-by-n matrix, then with high probability, any circuit, arithmetic circuit, C computing AX has size, omega of, so n squared will be the trivial algorithm, but actually the bound will give us something that's slightly less, like n squared over log n. Okay, so basically what we're saying here is that for a generic matrix, for most matrices, if I want to realize A times X by this type of an arithmetic circuit, we need essentially, naive size. So n squared is a trivial number of operations you do here, just one by one, multiplying A times X. And we can prove that for most matrices A, you cannot do much better. But of course, we don't usually care about random matrices A. What we care about special matrices A that actually correspond to computation we actually want to do, like FFT. And the question is, can we prove that FFT actually requires n log n size, or maybe it's better? So again, another fact here is that because FFT has a linear n log n operation, so FFT can be computed by a circuit size order n log n. Okay. By the way, another minor point here, if we go back to this drawing of the circuit, usually when we measure sizes of graphs, we might sometimes care about not counting nodes, but counting edges. But notice here, it doesn't make a difference because we're assuming every node is in degree 2. So the number of nodes and edges are the same up to a factor of 2. So up to constants are the same. So it doesn't really matter if we count nodes or if we count edges. Right? So just small minor point. So now the question is, can we prove it? So now the question is going to be, the main question we're going to study is taking these first facts and asking either a property of a matrix A that would allow us to prove it's hard. So either a property of a matrix A that we identified, we can say, oh, this matrix actually requires something close to n squared, size, or not. So that's going to be the question we'll try to study. So maybe before I do that, let me ask, are there any questions so far about this model of arithmetic circuits, about everything we discussed so far?
What does sparse in 2 sparse mean?
Oh, 2 sparse just means that my internal nodes only has 2 inputs. Like for example, here this node of Z1 plus Z2 can only take 2 inputs and compute the linear combination. So we don't allow nodes to compute the linear combination of more than 2. But if you're allowed to do that, then of course you can do everything in order n size. Let's say Y1 is some linear combination of the inputs and Y2 is some linear combination and so on. But then it's a linear combination of n inputs. So it's not a very realistic notion of like a basic operation. So you want a basic operation to have constant size.
Okay.
The minimal size. But you could also try to say, well, if the coefficients are very large or very small, maybe you pay extra for it. Maybe that's going to be another model. It's even more refined. But for our model, just the coefficients don't really matter. They're for free. But we want sparsity.
Shahar, I'm curious, what is the, so you said we don't know any superlinear bounds on an explicit operator. What's the, I'm wondering what the state of the art kind of in this area is.
I don't remember, some constant times n.
But there's no like somehow restrictions or finer models or something where we can
there are restrictions where you can prove stronger lower bounds. Like for example, if you bound the depths of the circuit, you can prove stronger lower bounds. Also, if you assume the circuit has no negations, you can only add things, never subtract. So it's like a monotone circuit, you can prove stronger lower bounds. But this just shows that, well, we need negations. And depth is important. Like FFT requires depth log n. So for depth log n, we can't prove anything stronger. For depth less than log n, sometimes we can, but even there, the bonds become weak very fast.
Okay, thanks.
Okay, thanks. Okay, so now let's move to this property. So turns out FFT has a very interesting property, which is all of its submatrices, k by k sub of any k, has full rank. So let me define this property. Now, so here's going to be the definition. So let A be an n by n matrix. We say, so A is called, let's call this super regular if the following thing is true for any k between 1 and n, and any two sets st in n of size k. If I take the matrix, let's call this AST. So what is AST? So here's the whole matrix A. This is S. This is T. So that's the following submatrix, right? That's going to be AST. So just a submatrix where the rows come from S and the columns come from T. So that's a K by K matrix. So this is full rank. So it says rank K. So again, a matrix is said to be super regular if all of its submatrices that are the same number of rows and columns have as large rank as they could potentially have. If it's a K by K submatrix, they have rank K. And here's another fact. The FFT matrix is super regular. Okay, so that's a very nice fact. It's not obvious. It's been rediscovered by people again and again in different communities. I think probably 5 different proofs of it at this point. Anyway, it's a nice fact to know. So if you take the FFT matrix, you take any submatrix of it, it's going to have as large rank as it could potentially have. And now the question that Valiant was asking is, can we use this to prove, superlinear lower bounds for FFT? Okay. What does it mean? Can we prove that any matrix is super regular? So here is such a property that we identified. It seems like it should be, if it holds the matrix, should be hard, right? It has as high rank as it potentially have, and all the submatrices are as high rank as they could potentially be. If a matrix has this property, can it still be computed by a linear size arithmetic circuit? Or maybe we can prove that any super regular matrix requires an arithmetic circuit of size that is more than linear. So that's going to be the question that we're going to investigate today. So is the question clear? Right, so from now on, we're going to forget about FFT. We're just going to think about this specific property that we identified about FFT matrices of being super regular and ask, is this property strong enough to prove a superlinear lower bound? So the first step is to try to ask, what can we say about the structure of an arithmetic circuit that computes a super regular matrix? Okay, that's going to be the first thing we're going to try and identify. So let's make another, I'm going to make another definition here. And that's going to be of something we're going to call a super-concentrator. it's going to be a graph. So a graph G VE. And we're going to also identify two specific sets in it. So I'm going to have I for and O for inputs. We're going to be in V of the same size. So this is called a super concentrator if it satisfies the following condition. So it's a graph G. So it's a graph, and we also identify I and O as two sets of n nodes in it. If this is the following condition, for any set S in I, maybe before that, for any k between 1 and n, and any sets S in I and T in O that have the same size k, there exist k vertex disjoint paths from S to T. Okay, so let's look at this definition for a second. So this is now this for a minute we forgot about in algebra. This is a definition of a specific graph structure. So we have a graph G, and again we sort of choose two specific sets of nodes I and O of some size n. We say this graph is a super concentrator. The following thing holds: take any subset of I and subset of O of the same size k. We can find k vertex disjoint paths from S to T. So by picture, so if this is I and this is O, and here we have another bunch of nodes, right, and edges and everything. So we're saying that we'll take any subset here S and any subsets here T of the same size. There is some way of connecting them through the graph by k paths that are vertex disjoint. Okay. Now, when we specify the set S and T, we don't specify their order, so you can still choose whichever. I might connect the first node in S to the third node in T, and the second node in S to the fifth node in T, and so on. But I want to connect all the nodes in S to all the nodes in T by k vertex disjoint pattern. So maybe let's see some example. I mean, maybe let's try to build it. Let's say I want to choose n to be 3. It's an example. Let's call an example. Actually, no, let's even do n equal to 2. Even a simpler example. So here's I, and here's O. And I want to connect them. So maybe first I do that. Is this a super concentrator? Well, let's see. If I take these two nodes and these two nodes, like all of I and all of O, yeah, they are connected, right? So by two vertex disjoint pattern. That's fine, but if I want to choose maybe these to be S and these to be T, then they're not connected. So this is not good enough. I need to add more edges. Maybe I'll do this now. Now this is still not okay because I can switch. Now I can choose maybe, you know, this to be S and this to be T. So I also need to connect this one, right? So well, that's just a complete graph, right? So trivially, we can, so if G is what's called K N N, so this is a complete bipartite graph. Because I have n nodes here, and all the possible edges in between them. This is, if I call this I and call this O, then this is a super concentrator. Right, but the problem is, but it has like n squared edges. And we see that the number of edges here actually corresponds to the side of the arithmetic circuit to try to understand. So the real question that's going to come up is, can we do it by adding more nodes in between them and reduce the number of edges from quadratic to linear. But I just want to point out that the complete bipartite graph is a trivial example of a super-concentrator. So now let me make the following claim. It's going to connect the two things. So let's see, be an arithmetic circuit that computes, AX, where A is some n by n matrix. So if A is super-regular, then C is a super-concentrator. Super-concentrator, meaning the graph of C. So where we know I is the inputs and O is the outputs. So again, that's going to be the main claim connecting these two notions. So if I have a super-regular matrix and I take a circuit implementing it, then this circuit has to be a super-concentrator, has to be this super-connected property. So the hope was that maybe we can do that, and actually this would allow us to prove that if you can prove that there are no super-concentrators with a linear number of edges, this would allow us to prove that for super-regular matrices, there are no arithmetic circuits with just, a linear number of edges, and then also a linear number of nodes, because there's the same up to a factor of 2. So this claim connects this linear algebraic equation to this graph theoretic equation. Okay, so let's see the proof. So the proof is going to be sort of like some of the proof by picture. So here, let me sort of draw two pictures here. So here's going to be the matrix A. And here's going to be the circuit C. So C is going to have n inputs, n outputs, and a bunch of computation in between, right? And of course, they're all connected. And now we want to say, well, we want to show that C is going to be a super-concentrator. So we want to choose a subset of the inputs here. Sorry. S. And a subset of the outputs, T. So S is a subset of the inputs. T is a subset of the outputs, and they have the same size. And what do we want to prove that we can find? So we want to show or to find K vertex disjoint paths from S to T in the graph of C, in the graph of this arithmetic circuit, right? So now we're ignoring the actual constant that we have in the gates. We're just looking at the combinatorial structure of this circuit. Okay, that's our goal. Well, what can we use? We can say, well, definitely we can use that if we look here on the corresponding matrix A, S, T, right? The rows being S, the columns being T. We know this has rank is K, right? This is what we can use. This is what we assume, right? That all the sub-matrices have full rank. So somehow we have to use this. How can we use this? Well, first thing what we want to do is just ignore all the inputs that are outside S and ignore all the outputs outside T. So step one. So let's fix any input outside S to 0 and delete outputs outside T. So really what we're going to get is just removing these inputs and outputs. Right, so now we have this sort of type of, let's think of it as a truncated circuit So here's again a circuit, but now the only inputs we see is Rs. And the only outputs we see are T, right? So everything else we kept as is, just so it's easier. And what this computes? Well, this computes a ST times X. Right, well, it's actually X on the coordinates in S. But okay, so just by fixing all the inputs outside S to 0 and deleting all the outputs outside T, we just compute the multiplication by this matrix AST. And now let's ask, well, how can we hope to find K vertex disjoint paths between S and T? To do that, we're going to use effect from or theorem from graph theory called Menger theorem. So Menger theorem connects finding vertex disjoint paths in a graph to the vertex cut of the graph. So this graph has K vertex disjoint pattern between S and T if and only if the minimal vertex cut separating S and T has size K. Right, so here I'm assuming S and T was of size K. So what is a vertex cut? A vertex cut is a subset of nodes that if I remove it from the graph, I kill all the paths between S and T. So for example, I can remove S. This is K nodes, right? Or I can remove T. That's another K nodes. Maybe there are less than K nodes somewhere inside C that I can remove. And if I remove them, I disconnect S from T. So I take the smallest subset, let's call the minimal vertex cut, separating S from T. And what Menger proved is that the maximal number of vertex disjoint paths from S to T equals the minimal size of a vertex cut. It's like a minimax type result, like like very similar, or actually a precursor to max flow min cut theorem. It's actually a special case of it. And I want now to use this theorem. So basically, if I want to show that this graph has K vertex disjoint paths, I want to prove that there is no vertex cut of size less than K. So assume towards a contradiction that the circuit has a vertex cut. Let's call this vertex, I don't know, U of size less than K. What does this mean? So let's do it by picture. So here's S, here's T. And here somewhere, there's the set U. And my circuit basically, I'll draw it like that. Somehow connected here, but everything has to go through U, right? So U is the vertex cut. So if I remove U, S and T gets disconnected. But I claim that if this happens, then I can factor the matrix AST as follows. It's going to be the product of two matrices, the linear algebraic map from S to U. So every node in U is some linear combination of the elements of S. There will be some matrix called this B, and the linear map from U to T. Let's call it matrix C. So again, why? Every node in U is some linear combination of the inputs in S. So it's represented by some matrix B. What's the size of B? So if the size of U is, let's say, L, B has size L times K, and C has size K times L. Right? Every node in U is a linear combination of the inputs, and every node in T is a linear combination of the nodes in U, because it's a vertex cut. There is no path going outside it. So this would prove that the rank of it, so if L is less than K, then the rank, so then the rank of AST is at most L, which is less than K, which is a contradiction for it being a full rank matrix. Right? So we just proved completely proving this claim. So again, just to recap, because the matrix AST has full rank, there is no vertex cut between S and T of size less than K. And then by Menger theorem, there must exist K vertex disjoint paths between S and T. And since this is true for every S in subset of the inputs and every T is subset of the outputs of the same size, this graph of the circuit is a super concentrator. Okay, so this finishes the proof. So maybe now is a good time to see if anybody has any questions. So again, so the main thing you should think about this claim doing is a sort of connecting two different things. We really want to study arithmetic circuits, and arithmetic circuits has to have two components: a combinatorial structure as a graph and the coefficient structure. And this claim basically forgets about the coefficient structure. It just remembers the graph structure of this arithmetic circuit, and it says if this arithmetic circuit happens to compute a superregular matrix, then this graph structure is very special. It is a super concentrator. Okay, so basically now we just reduce to studying super concentrators. But notice we did forget something. We forgot the coefficient structure here. So just wanting to keep in the back of your mind. So now we're going to move to this next question that Valiant was asking. So what do we know so far? We know that if C computes FFT or any other or any superregular matrix, then C is a super concentrator. Right, and now here's going to be the main question. So again, think of C with these inputs and outputs. Is a super concentrator. Okay. Are there such graphs? With order of n edges. Right, that's going to be the main thing we try to prove, or disprove. Asking, we really want to prove that FFT cannot be done in a linear number of operations, but we're trying to prove lower bounds. So we said, well, FFT, whatever circuit you can come up computing it, must be a super concentrator. In particular, the one that we actually implements FFT in n log n edges is a super concentrator. But can we actually build such graphs where the number of edges is not n log n, but order n? Right? If the answer is no, then we just proved that FFT cannot be implemented with a linear number of operations. It should be a major breakthrough. So since we don't know how to prove it, then you might guess that the answer here is, yeah, there are such graphs. So the answer is going to be there are such graphs, and they can be built. They can be built using expanders. Okay, so that's going to be the next part of this talk. We're going to see how to use expanders to construct super concentrators with a linear number of edges. Okay. So really what this does is it refutes, it sort of kills this direction, because we can actually construct super concentrators with a linear number of edges. So it shows that this direction maybe is futile. We cannot use this direction to prove that linear algebra requires more than a linear number of operations. Now this is, but there is some light at the end of the tunnel here, because you can use similar techniques to prove that if you put extra restriction on the structure of this arithmetic circuit, like for example, you bound its depth, then actually you cannot do that, and then actually you can prove a superlinear lower bound. I mean, I'm not going to talk about this in this class, but you should just be aware that by putting more restrictions, you can actually prove a superlinear lower bound. So for example, we can prove that FFT cannot be implemented in order n, operations and a constant depth, like constant parallelism. This is known to be true, but still the best trade-offs are still, I think, very far from now. Okay, any questions? Because the next part is going to be somewhat separate. We're going to define bipartite expanders and vertex expanders and show how to use them to construct super concentrators. That's going to be the next half hour. Okay. Good. So now the next topic, so this topic is going to be a good motivation to define what's called bipartite expanders. So then before doing that, let's just define bipartite graphs. So in this talk, for this part, we're going to talk about bipartite graphs. So we usually denote them by G being, so I'll do it by LR, left nodes, right nodes, and edges. So it's going to have nodes on the left, nodes on the right, and some edges in between them. So you can think of the edges as just some subset of L times R. Right? It's a bipartite graph. We're also going to assume throughout, so I'll make the following definition. An NMD graph is a bipartite graph G U V E with the following condition. So, sorry, not U. So let's stay with LR. So the nodes on the left have size n, the node on the right has size m, and actually for this application, to actually be important that these numbers are different, and each node V in L has degree D. Okay, so we're going to be assuming that it's sort of, the picture you should have in your mind is here's L, here's R, every node in L has degree D. This is size N, this is size M. Okay, in particular, just to verify we're all on the same page here, the number of edges here is ND, right? Because we have N nodes on the left and each one has D edges going out. And I also use the following notation. So we're going to use the following notation. Given a set of nodes on the left, so the neighbors are denoted by gamma of S, which is a subset of the right-hand side. Right. So given a set of nodes on the left, S, gamma of S is going to be all the neighbors, which, because it's bipartite, are going to be on the right-hand side. Okay. So far I haven't defined expansion, just bipartite graphs which are left regular. Any questions so far? Okay. And now we're going to define the notion of an expander. So let alpha be a number between 0 and 1, and beta which be a positive number. So NMD graph is, let's call it an alpha beta expander. It's really going to be a vertex expander. If the following thing is true, for every set of nodes S on the left, whose size is at most alpha n, the number of its neighbors is at least beta times size. Okay, so that's going to be the crucial definition here. And what does it mean in my picture? So if here's my graph, left and right. I take some set of nodes here on the left, S, and ask, well, how many neighbors do they see here? It's gamma S. That's going to be big. It's going to be at least a constant fraction of the side of S, and the larger beta is, the better the expansion is. And the larger alpha is, even larger sets expand. Okay? And specifically what we will need for this construction is the following claim. And concretely, we're going to use alpha being a half and beta being 1. So there exists, okay, for every n, or let's say for every, let's say large enough n, there exists, so it's going to have n nodes on the left, 3/4 n nodes on the right, and some constant degree graphs which are half 1 expanders. Okay, what do we do again? So we have n nodes on the left, we have less nodes on the right, but still every set of nodes here was somewhat smaller than 3/4, let's say a half here. That's going to be at most n over 2. If I look at its neighbors here, it's going to be at least as big. It doesn't shrink. So even though the right-hand side is smaller than the left-hand side, still every set of at least half the nodes on the left see at least that many nodes on the right. Okay, so I'm going to skip when the claim is given here on the nodes. It's basically a probabilistic method proof. I want to first show you how we use these graphs to construct our super-concentrators, and then if you have time towards the end, I'll show you how this. The construction is not a construction; it's just a randomized construction, and choose a random NMD graph and analyze this probability of it failing to be this half 1 expander. So I'm going to defer on that for a second. First, let me show you how we use them, and then if you have time, I'll show you how to prove this claim. I want to show the construction. So we're going to construct. So we're going to construct GN. GN is going to be maybe GN is going to be a super-concentrator with IN inputs and outputs of size n. And we're going to do it recursively. And we're going to need 2 steps. Let's set m to be 3n over 4. And let h be this n, 3n over 4 d graph, which is a half 1 expander that the previous claim says exists. Maybe it doesn't construct it, but it exists. And we're going to use this, and we're also going to use GM. So GM is going to be a recursive construction for a smaller value of m, right? 3n over 4. How does the construction look like? So first we're going to have n nodes here. going to be n nodes here on the left, n nodes here on the right. That's going to be our IN ON. And here I'm going to put GM. In the center, again, here we're going to have M nodes for its inputs and M nodes for its outputs. Well, the obvious thing is we're just going to place H here, one copy of H here, another copy of H here, right? And then we need to do one more tweak, which is we need to add the matching from the inputs to the outputs. So let's say if I denote them here are my nodes, I'll also connect the first to the first, second to the second, third to the third, and so on, up to the last. So this is a construction. So it's a recursive construction. So to construct this graph on n nodes, n inputs and outputs, and some number of intermediate edges, we recursively do it for side m, which reminding you m is 3n/4. So smaller by n by a constant factor, and this graph h. So let me first prove to you why this is a super concentrator, and then I'll count the number of edges it has, which is going to be linear in n. So why is this a super concentrator? So let's then look on, and then we still do it by picture here. Let's look on a set S here and a set T here, with the size of S and the size of T as size K. So first case is going to be, what if K is at most n/2? In this case, I claim I can find a set here, S prime, and a set T prime here of the same size, such that there is a matching here between S and S prime and T prime. Y we'll see in a second why. Okay? But assuming that, now we can just recursively use GM to connect S prime and T prime. So maybe now is a good time to ask, well, why is there a matching between S prime and T prime and S and T prime? S and S prime, T and T prime. So let me take one step back and go back to this half-1 thing. So maybe I use here. Maybe use here a different color, green. So let H is a half-1 expander. So here's going to be a claim. So H is going to be left, right edges. So the claim is going to be, so if S is a subset of the left-hand side of size less than n/2, then exists a matching from S to the right-hand side. So again, so if this is S, maybe I'll do here the picture. If I choose here a set S of size at most n/2, there is some way of connecting it to the other side by a matching. Why this is true? Because this is exactly the proof here again. Is Hall theorem. The Hall theorem is again a theorem in graph theory. It tells you when can you find a matching in a bipartite graph, and its conditions are exactly the conditions. Every set on the left-hand side, its neighbors on the right-hand side is at least as large. So again, I mean, so if you read the conditions of Hall theorem, it is exactly this one expansion, that every set of nodes, its image is at least as large. But I mean, so this is like a small minor point. Let's ignore this for a second. I mean, we can review it later if you want. But I just want to finish this construction. So believing that for a second, we're saying, well, if K is at most n/2, then there's actually a matching here from this big side n to this smaller side. So let S prime be the image of this matching of S, and T prime be the image of the matching on T, and then recursively we can connect them through GM. So this was part 1. Notice here we didn't use this red matching at all. The second part says, well, what if now K is more than n over 2? Well, now we're just going to use a matching. Notice if I have K nodes, maybe this here. If here's again. This is again, you have n nodes here, and n nodes here, and I have here a subset S and a subset T. And the size is the same, it's K, and K is more than n over 2. There must have some joint elements, right? So the side of S intersected T, if I sort of try to, if I match them, if I look at this matching that we created here, so we identify the first node here with the first node here, and the second node with the second node. So I claim that there must be at least 2K minus n edges in the matching with the left node in S and the right node in T. This is by sort of counting, right? I mean, if I want to evade all the best, if I want to evade, you know, S is at least S edges and T is at least T, and you know, so it's just a simple calculation that you know there must be many edges that are so hit both by S and by T. So if we believe this for a second, what do we get? So we can, these nodes from S and T, we can just directly connect. So let's remove them. So let S prime in S and T prime in T be those obtained after removing them. After removing the nodes which are directly connected by the matching. So I claim that this, what is the side of S prime? Well, it's K, it's at least K, minus the nodes we remove, 2K minus N, which is N minus K, which is, sorry, it's not the other way around. S prime is at most. It had K nodes, and we removed at least 2K minus N edges. So could we connect these nodes directly? So this is N minus K, and because K is more than N over 2, this is less than N over 2. And similarly for T prime. So now we just reduce to the first case by connecting these nodes directly to the matching. We reduce to the case where S and T have size less than N over 2, where we go back to this first case. Okay, so and this finishes the proof. So again, there are a couple of things that we still have to do. So then I still want to show you why there is this matching for this whole condition, and also still need to prove to you why this graph H exists. But modulo these two facts, this gives you the full construction. So are there any questions at this point before I show these two things? Okay, so let me just, again, I know this might be a bit fast, so this is why we have the notes. We can also review them later. And so first, let me just show this claim here, just write it more formally here for this matching. So let H be a F1 expander. Then for every set of L whose size is at least N over 2, there exists a matching from S to R, meaning that the way for every node in S, choosing a distinct node in R. What does it mean? I.e., for every node, V in S, we can pick a distinct neighbor. Let's call this maybe pi of S in R, where all these nodes So pi v, v in S are distinct, different, and v, pi v hidden edge. So every node in S, we can connect to a node in R. Right? This is and again, the proof here is exactly Hall theorem. The Hall theorem is a theorem that tells us when there is a matching in a graph. And the proof is that, again, by Hall theorem, a sufficient condition, in fact, an equivalent condition is that for every, let's say, subset S prime of S, it has at least the number of neighbors is at least a set of S prime. So this is exactly Hall theorem, and this is exactly the condition we have within it's a half-1 expander because S has size n over 2. So S prime has size at most as n over 2. So it holds by assumption. So again, all I'm saying here is that this is just exactly the same conditions as in Hall theorem. I'm not going to prove Hall theorem here. You can check it online if you want. So this is one ingredient. The last ingredient that I want to show you in the last 7 minutes is, again, it was this claim that, that for some, if D is for some constant D, or let's say that there exists and 3n over 4 F1 expanders. What does it say again? And the proof is going to be by the probabilistic method. So what are we going to say? We're going to say, so I'm going to just construct this graph randomly. I'm going to have n nodes here, m nodes here when m is 3n over 4. And I'm going to connect for every node v here. I'm going to randomly choose d neighbors. And d is going to be some constant that we're going to choose later. So for every v on the left-hand side, we're going to choose d random neighbors in the right-hand side. So we have a random graph. And what do we want to? We want to analyze the probability that the graph is not a half-1 expander, and we want to prove that this is really, really small. So most graphs that we choose in this way are going to be half-1 expanders. How can we do it? If it is not, then there exists a set S in the left and a set and a set T in the right, whose size is some parameter K being at most n over 2, where all the neighbors of S lie in T. Right? So again, in fact, here we can say S has size K and T has size even less than K, but this is also included by this concept. If this graph is not a half-1 expander, then there must be a set S on the left-hand side of some size K and a set T on the right of the same size K, such that all the neighbors of S lie in T. So now for every S and T, we're going to show this is really, really, really unlikely. And then we're going to union bound over S and T. Okay. So what is this probability? What's the so given S and T, what's the probability that all the neighbors of S lie in T? Well, how do we choose these neighbors? For every node in S, we choose its D neighbors completely at random, uniformly. So it's going to be the number of choices in S, if they're going to be in T, it's going to be T choose D over M choose D. Right? That's the number of choices for a specific node in S. That, out of all the possible choice of D random neighbors, M choose D of them. the fraction of those where all these d neighbors land in T is T choose D. So you have that to the power S. And then, just simple manipulations would give us some bound here. Let me just, where is this? So you want to bound this. So that's going to be smaller than T over M to the ds. And remember, the set of T is at most n over 2, the set of M is 3/4 n. So that's going to be smaller than 2/3 to the d. Actually, no, I might just want to keep it as this for now. Sorry. Let's just keep it as this for now. Okay, this is just okay. That's just one bound. And now I want to union bound. Over all S left, T right of size K. So what's going to be the probability? So we're going to have the sum over K from 1 to n over 2. How many options do you have for S? N choose K. How many options do you have for T? M choose K. And now what's the probability that all the neighbors of S lie in T? Which is what we wrote here. K over M to the dk. And now if we just want to simplify it a bit, it's going to be at most the sum over K from 1 to n over 2. So N choose K is at most En over K to the K. M chooses K is at most Em over K to the K. And now we have K over M here again to the dk. So it's a bunch of things to the power K. So you can take this power K out. It's going to be En over K times Em over K times K over M to the D to the power K, right? Now I'm just reminding you that M here is just some 3/4 n, so it's just some constant times n. So we can just replace M by n everywhere, and also n by m. So that's going to be equal to the sum of some constant here that you can compute. I think what I got here, and then we can replace this n by m. So it's going to be K times M to the D minus 2 to the K. Right, because again, n is some constant times m, and in fact, if you do the calculations, then you get this is sort of smaller than 10 here. Okay. Again, this m over k cancelled, and n over k is just a constant times m over k. And okay, and now let's see, this is just in k is at most n over 2, m is 3/4 n, so this is smaller than the sum over k, again from 1 to n over 2, 10 times 2/3 to the d minus 2 to the k. So you see, by choosing d large enough, this 2/3 to the power d is going to be, or d minus 2 is going to be less than 0.1. That's this geometric sequence that converges. And concretely, if we choose d to be 20, then this is going to be less than 0.01. I mean, you can probably get this all with smaller d, but that's good enough. So this finishes the proof. I mean, if you want, the notes contain the full calculation, but that's basically all the calculations. So what we use here, there's this what's called the standard probabilistic technique, where we say choosing a graph randomly allows you to prove it has very strong pseudo-random properties. And here, these properties will be in this half-1 expander. By the way, getting these graphs explicitly is hard. Spectral expansion can only guarantee much, sometimes weaker vertical expansion, not always that strong. So, but we don't care. We just want to show existence, right? So now we can use these graphs to construct these super concentrators with a super linear size. I mean, we'll be out of time, so let me just sort of finish here. I know I was a bit sort of quick on a few points, but hopefully you got at least a high level picture here. So again, just to another 2 minutes, just recap. So we're trying to study lower bounds in linear algebra. To do that, we identify these properties. First, we define this formal model of an arithmetic circuit. We identify this property that the FFT matrix is super-regular. We use this to identify a graph theoretic property related to it of being a super-concentrator. That was the first half of the talk today. And then the second half was to construct super-concentrators with a linear number of edges, where one ingredient was this half-1, expander set of a constant degree, like here 20, and then a recursion. And we had this construction here, that again, we also explain in the notes, where we combine recursion with adding this matching on top, and the simple case analysis to show why this is a super-concentrator. So again, I think the one message you can get from that is that expander graphs are very useful, but here if you see the expander graphs are sort of a bit different than the one we've seen so far. First of all, they're bipartite. And also it was important that they're not balanced. So one side was significantly smaller than the other side. Like M was much smaller than N by a constant factor. That was crucial in the application. The application Max is going to show us on Thursday is going to have very similar flavor. We're going to use this type of unbalanced expanders to construct good error correcting codes. And also there we will need this type of vertex expansion, but with different parameters. Okay, questions?
We needed M to be a constant fraction for the number of edges in the construction to be linear. Is that?
Yes. Oh, that's right. I didn't analyze the number of edges, so well, maybe just do it now. So what's the number of edges of Gn? Well, it's the number of edges of Gm, right? Plus twice the number of edges of H, plus N for the matching. The point is that this is going to be order N, because H is a linear number of edges, and M is smaller than N by a constant factor. So this converges to be an order N. And here it's crucial that M is some constant N, where C is less than 1. Like the 3/4 doesn't really matter. Any constant less than 1 would be fine. So that this would converge. Yeah, thanks. But notice this is really an unbalanced expander, whereas all the expanders we've seen so far, all the algebraic ones we know to construct give you balanced expanders, not unbalanced expanders. But unbalanced were crucial in this application, and also in some other applications. Yeah, more questions?
I think you mentioned that it's hard to construct this kind of like bipartite expander, but like why can't you just like pick a bunch of random graphs like of this, like constrained by this, and then like wouldn't that give you like an expander of this form? Or
yes, I mean, so what we proved here towards the end, if we choose this H randomly, it's going to work. But this doesn't give you a construction. This shows that, well, more things are going to work, but I want to actually pinpoint one construction that I can actually guarantee works. And I think this is much harder. So it's very common that random constructions is very easy to analyze them by some simple probabilistic techniques, but constructing them explicitly becomes much, much harder. Oh, it's a very common phenomenon.
Randomness is a computational resource, right? You don't always have randomness to work with either.
Yeah, right. Yeah.
Also, imagine that you want to design this for, let's say, like what we'll see on Thursday is a similar thing where we use such a graph to construct a code. Now, think about the code. I want to put the code in some, standard. Well, we all have to agree on this code. It means we all have to agree on this graph. We can't just say, I'll choose a random graph. Hopefully, it's going to work. We want one that we know we can explicitly define and that we know is going to work, not just hope it's going to work, right? So that I think even the question of given a graph H, very fine sum expander in this sense is, as far as I know, computationally hard. And the main benefit of using spectral expansion is that it's easy to check algorithmically because it just involves linear algebra. But these combinatorial questions about edge expansion versus expansion, we don't know of good ways of verifying them computationally. And to some extent, sometimes people can even prove that they are hard under some models, under some assumptions, and so on.
I see the distinction. Thank you, Professor.
Sure. Any more questions? Okay. So maybe now is a good time to start. I'm sorry for running a bit over time, but I really wanted us to finish this today. So next one start on Thursday with a clean slate, you know, on this new application, other application. Okay, so I guess that's it for today. So I'll stop the recording and thanks everybody.